This video is on biconditional statements. So we've seen that the conditional statements P implies Q and Q implies P are generally not logically equivalent. So for example, if we've got the open sentence P being X is an integer multiple of 10 and the open sentence Q being X is an even integer, then P implies Q is true, but Q implies P is false. So if X is an integer multiple of 10, then it will also be even. If X is even, it is not necessarily a multiple of 10. So we call this reverse the converse. So Q implies P is the converse of the statement P implies Q. So just for some quick practice, for each of the following statements, I'd like you to first write the converse of the statement and then determine whether that converse is true. So here are the two to try. If an integer x is odd, then the integer x is not divisible by 2. And if a car's battery is dead, then the car will not start. So take a quick pause there and try those out. All right, let's first write the converse of this statement. So this is just reversing. If the integer x is not divisible by 2, then it is odd. So that would be the converse. And in this case, this converse is true. If an integer is not divisible by 2, then it will be odd. An integer is even if it's a multiple of 2. An integer is odd if it is not a multiple of 2. So in this case, both the original statement and its converse are true. Next, if a car's battery is dead, then the car will not start. So the converse of this would be if the car won't start, then the battery is dead. So I'd say that this statement is false. The converse is false because there could be other reasons the car won't start. Maybe somebody took the engine out. I don't know, just there could be a lot of reasons that the car might not start other than the battery being dead. So this if-then statement is false, whereas I would say that this statement, if the battery is dead, the car will not start, we could say is true. Okay. So we see that sometimes both P implies Q and Q implies P are both true. Sometimes it's not the case. But if it is the case, then we write this as P if and only if Q. So this is like a double arrow, P if and only if Q. And so as an example, an integer x is odd if and only if it is not divisible by 2. That's a true statement, and this is called a biconditional statement. It's conditional in two directions. So I'd like you to, again, take a pause and determine the values in the truth table for P if and only if Q. On the left, we've got all the different possible truth values of P and Q together, and I'd like you to fill in the truth values of P if and only if Q in each of these cases. So give that a quick try. All right, so if P is true and Q is true, then P implies Q and Q implies P are both true. If P is true and Q is false, then P implies Q is false, right? So P implies Q is false in this case, so false. If P is false and Q is true, then that means that Q implies P is false in that case, so this would be false. And again, now if P is false and Q is false, then let's see, P implies Q is okay. We made a promise with P, but that first piece turned out to be false, so the whole statement is automatically true. And Q implies P is also okay. So we made a statement with Q. That statement was false. A false thing implied a false thing. That is acceptable. This promise was not broken because the first piece did not hold. So this is true. So that's our truth table for P implies Q. Basically true when the values match and false if the values do not match. So similarly to when we looked at different ways of phrasing P implies Q, we also have different ways of phrasing P if and only if Q, or this double arrow, P if and only if Q. So one way of saying that is P is true exactly when Q is true. Makes sense, I think, especially given the truth table above. Another is P is necessary and sufficient for Q. Why is that? So P is necessary for Q. That's equivalent to Q implies P, because for Q to be true, it is necessary that P is true. And so that means that if P is false, then Q cannot be true. Sufficient, that's P implies Q. And so P is sufficient for Q. In other words, if P is true, then Q must be true. Now let's break down this phrase that we're usually using, P if and only if Q. That's how we usually read this phrase out loud. So that's really in two pieces. So this is P if Q, and also P only if Q. So this P if Q, that's the if Q, then P part. So P if Q, then P. In other words, Q implies P. That's that piece of it. P only if Q, that is, if we break down what that means, that's saying P can only be true if Q is true. So P can only be true if Q is true. So this is the P implies Q part. Why is that? If we think about this P implies Q, then P can only be true if Q is true. If Q is false, then P cannot be true. This entire statement would be false. So that's the two pieces, P if and only if Q. P if Q corresponds with Q implies P. P only if Q corresponds with P implies Q.